more complex. And so what we want to prove for the first half of the class is something similar to the DC theory, kind of theorem, which is, if I look at the average, remember what this is. This is the average of f under the empirical. This is just the sample average, and this is the theoretical average. But the maximum of this, so before we bounded that in terms of DC dimension or something like that, now we're going to show that it's less than or equal to 2 times the Rademacher complexity of the class F, plus this extra 1 over root n. So this is on the notes, page 112. And the proof is actually quite a bit simpler than the DC proof. So the proof goes like this. There's 2 stages. Let's first of all define the function g, which is actually a function of all the data, which is this thing we're interested in, the supremum of sample average and the true average. So because this is actually 1 over n sum f of zi, it's a function of all the data, right? It's a function of z1 to zn. So this g is a function of z1 to zn. And this proof will show you a technique that's used quite a bit, which is first let's show that this random quantity is close to its mean, and then let's bound its mean. So that's a common strategy in a lot of these concentration of measure ideas. So first of all, the proof that it's close to its mean we've already actually done. It's almost trivial now because we're assuming f is a class of bounded class of functions, or I should say a class of bounded functions. And for simplicity, let's say we do 0 and 1. Then what happens to anything in here if I change one observation? What's the most I can change d by if I change one observation? Keeping in mind this is between 0 and 1, well, the most you can change by 1 over n. Right? So this entire complicated thing can only change if I wiggle one observation by 1 over n. And hence we use McDermott's inequality, which was like Hoeffding's inequality, but for more general things than sums, which said, remember, as long as I change one observation, nothing changes much, then we get the concentration around the mean. So McDermott's inequality says that the probability that g minus mean is bigger than epsilon was, it looked just like, and to rewrite, if I set this equal to delta, I can rewrite this by saying, therefore, the probability at least 1 minus delta, we have that g is, let's say, no more than its mean plus so that comes again by just setting this equal to delta and solving for epsilon. So you can see we've proved part of the theorem, right? I've got this, which is g is less than or equal to, and I have the mean of g plus this term. So clearly, what I'm going to do now is show that the mean of this complicated thing, is bounded above by 2 times the Rademacher complexity. Okay, everybody with me? So let's do that. Well, we're going to use a similar trick as we did in the DC theorem, which is to introduce a ghost sample, once again. So we imagine a second completely independent sample. And of course, now if I'm going to write Pn prime of Fn to be the sum of the average over the ghost sample. Of course, the average of this is still the original average, right? So we know that the expected value of, with respect to the randomness of the z prime, which is the same as z's, is still the original. The expected value of this is just expected value of any one of them, but z prime has the same distribution as z. So this is still just literally write out, let's go back to what G is. The expected value of G is the expected value, let's just put in the definition of G. It's the suit of, let's say P of F. Now what I'm going to do is take the n of f, which is this, and just replace it with this. So that's how I sneak in the dose symbol. So this is E prime, En prime, now, I claim that I can pull this expected value, which is the expected value over z1 prime, z2 prime, z3 prime. I claim I can pull it out, and I can only make things bigger. So I'm claiming that this is less than or equal to expected value over the original sample, expected value over the ghost sample of what's left over. So this is the suit. So let's convince ourselves that's true. See, look, what I did is I pulled that out. I said that can only make things bigger. Well, if that's not clear, then you should go away and think about it. But let me just put a simpler version of this now. Suppose instead of taking the soup over a whole bunch of functions, I was just taking the soup over two functions. That is the maximum over two functions. Then this claim is equivalent to saying that, say, the maximum of two expected values, let's say the expected value of x and y, the maximum of these two numbers is less than or equal to the maximum, less than or equal to the expected value of the maximum. And I hope that's pretty easy to see because we know x is less than the maximum of x and y. That gives you one of them. And we know y is less than the maximum. And therefore, if you take the maximum, you get that. If that's not clear, you should go and think about that for a minute. There's nothing complicated, but this is just a fancy version of that. You notice if I have the max expected value, I can make it bigger, but I fully know the expected value. So I'm just doing exactly that, except over an arbitrary class. Yeah.
So, like, aren't there doing some pattern in the ghost samples when you say that expectation of P dash NF is equal to CF?
From here to here?
From the second statement that you have encircled, the expectation above.
This one?
No, the leftmost encircled.
From here to here?
No, above that.
Here?
Yeah.
No, this is always true because let's write down what this means. So let's write down what this is. This is the expected value of 1 over n of f of ci prime. But the expected value of an average, since our ID is just the expected value of, let's say, one of them. But z1 prime has the same distribution as z1, so that's the expected value of, say, f of z, which is exactly what you do. It's because we're assuming they're all IID drawn to the same distribution. Just for clarity, now let's write out more precisely what these things are. So this is the expected value of soup 1 over n prime writing up the definition of Pn prime and Pn, they're the empirical averages. And now comes the critical step. You know, these are all IID again, right? I just have these two lists of IID, everything's independent, I can switch things around. So if I have, think of the numbers as being like this, everything's drawn from the same distribution. It doesn't matter, I can switch this one and this one, I can switch this one and this one, I can switch this one, it doesn't matter, right? Everything's the same, they're IID. They're all independent, identically distributed. So in particular, switching the order of this doesn't change the expected value. Right? Expected value of x minus y and expected value of y minus x are the same if they have the same distribution. So what that means is if I throw a random sign change in there, namely a Rademacher random variable, it doesn't change the expected value. Is that clear? It either, if it's a +1, it leaves it alone. If it's a -1, it switches it, but that's the same distribution. The distribution of z1 minus z1 prime is the same as the distribution of z1 prime minus z1. They're equal in distribution. So that doesn't change the expected value there. And now, all we do is the triangle equality. Because I can bring the sigma I in here and the sigma I here, and I have something minus something else. But that's less than or equal to the first one plus the second one. So I'm just going to do that here. That's less than or equal to. So I'm going to look at the first one and the second one. Well, the first one is this, expected value of soup over F. What happened to this E? Well, this first term doesn't involve the ZIs. Right? It only involves ZI prime. So taking the expected over the Z's doesn't change anything. Similarly, the second one doesn't involve the Z primes at all. It only involves ZI. So when I take this expected value, it doesn't do anything. It just leaves this expected value. That these two terms are identical. This is the definition of the Rademacher complexity. So is this. So this is 2 times. And we're done. Yeah.
So I followed that when you replace P of F by the expectation, right? Expectation dash of P dash NF. But why is the expectation both over P dash M and P of M? Should it be only on P dash M? In the third line from the top, one line above that, yeah, there the expectation should only be on P dash M, right? Not on both of them.
Well, that's fine, but it doesn't hurt to put it there.
But then if you take the expectation of P of M, then it also becomes P of F, right?
No, because this is only
okay, I see.
over the
I see.
lines, right? Any other questions? So this is actually kind of a very slick theorem because it's very similar to the DC theorem. This is the ghost sample, but it's much shorter and simpler. And just breaking it up into McDermott plus bounding the expected value using this process of adding a ghost sample and putting in the Rademacher random variables is usually called symmetrization. And it often makes things much simpler. And oh, you're right. Ah, sorry. Thank you. I dropped the sigmas. That's critical. Yes, keep a close eye on. So I'm bringing the sigmas close. And one thing I mentioned the other day is that if the DC dimension is finite, did I mention this in the other class? if the VC dimension is finite, if the VC dimension of that, let's say, is equal to D, then it can be shown that the Rademacher complexity is less than a constant times the over root n. So what that means is we've also proved the VC theorem now. This is an alternate way to prove the VC. The proof of this is actually a little bit complicated. That's theorem 7.77. There's a simpler theorem, 7.75, which gives a slightly weaker bound, which will involve a log term. It'll end up being, I think, d log d over n. And that's theorem 7.75. I'm not going to prove it, but you see it's very short. All it does is it uses the fact that if script f was a binary for binary functions, then when you think about these Rademacher sums, they can only take on finite many values. This can only be 1, 0, 1, 0, 1, 0, 1. This can only be minus 1, 1, 1, 1. So you can do a counting thing over the possible arrangements followed by hoofing and get it, and that's what theorem 7.75 does. But there's a sharper bound, which is this one, which uses more advanced techniques. The proof is not in the notes. However, you should be aware that these are bounds. So it's possible that the VC dimension could be infinite, and the Rademacher complexity could be finite. So therefore, this is actually a sharper theorem. Yeah.
Have we made a strictly weaker assumption than we haven't? Sorry, I've lost track of which assumptions we made.
The assumption we made in this theorem was that script f was an arbitrary class of bounded functions.
Between 0 and 1.
Once you say bounded, you can pick any numbers you want. I picked 0 and 1, like uniformly bounded. So we're not assuming they're binary, so it's weaker than the VC theorem. But we are assuming boundedness right now.
So you mean weaker meaning more generalizable?
Yeah, it's more general. Speaking of which, let's talk about a little bit more generality. So, yes.
So the reason you can include the sigma I is because we are taking the supremum, the only assumption about if that is bounded. Is that the reason?
No. I'm just saying, let's suppose x and y are draws from a common distribution. Then I claim the following quantities all have, I claim that x minus y is equal in distribution to y minus x, which is equal in distribution to a Rademacher times x minus y. That is, I claim the CDF of this is the same as the CDF of this is the same as the CDF. So I haven't changed anything in distribution, that's any expectation, but therefore I haven't changed any expectation. Any other questions?
So why do we still use VC theory? Is it sometimes easier?
Oh yeah,
VC dimension?
if you already have a class, you know it's a VC dimension, you might as well just use the VC theorem.
Because of the Rademacher complexity is hard to figure out.
So one thing about the Rademacher complexity is how do you compute it? And it can be very, very difficult, and it's like one of the ways to compute it. It's like, oh, it's bounded above by the VC dimension. There's other bounds too, but it's VC dimension is something we often know, and the Rademacher complexity may or may not be. One example of this, I don't know if I'm in this class, but is proving things about King's clustering. There are two proofs about properties of King's clustering. One uses VC dimension, gives you one bound, and one uses Rademacher complexity, gives you a different bound, and you can actually take the minimum of the two bounds. So I think we'll make that work.
Suppose we can draw randomly, uniform randomly from the function class f. Can be used like a finite approximation of this Rademacher complexity and bound it so that we have a sharper upper bound.
Yeah, that's interesting. So is there a way to actually, if I give you a function that's maybe some numerical way to compute the Rademacher complexity?
And we can actually show concentration over, like say that the numerical level when n gets large, it converges to these two terms.
So I've never seen anybody do that because these function classes usually are pretty complicated. And
The specific function class is like this kernel expansion, we have these class trick, which is essentially the same thing from the function class and then
The kitchen sink.
yeah, it's an extension of the menu. Similar idea.
So that's an interesting idea. I mean, you'd have to prove something about how, so you could try to do a random sample of functions somehow, compute this thing, and then you'd still need to prove, though, that that's close to what you're trying. So there would still be some work to do. Maybe people have done that, I'm not sure. I haven't seen that, but it's possible somebody's done that.
But then how would that help? Like, I don't see why that.
Well, suppose you don't know that Rademacher complexity. He's saying maybe you can estimate it. So, yeah. So I don't know, maybe somebody's done it. I haven't seen it, but perhaps it's been done. We are going to do something similar to that in a minute using covering methods. But that's different, a little bit different. That's an interesting idea. So the main goal here, the concentration measure, was to get 4 theorems in, which we did already. So it's Hoofding, Bernstein, the DC theorem, and the Rademacher theorem. Those are the 4 key things. Everything else in concentration measure, well, not everything, but most other stuff in concentration measure is some version of this or extension of this. It's not 100% true, but it's pretty close to true. And also, this shows you all the kind of tricks, the techniques that you need to know. I do want to mention some other stuff that we're not going to go into in great detail, but I at least want you to have heard of it. So if we were doing a whole class on concentration measure, we'd go into these other things in great detail. So we're not going to do that. But I do want to mention them, which is other measures of complexity that are even a little bit more general. Okay, and this kind of relates to the he said, and one of them is covering numbers. Okay, so this is another way, kind of more general way to measure complexity. It's funny, I did. Okay, here it is. So, it's written this way. Okay, here's one way to write it. Some people write it though like this. So what is this thing? Well, first of all, we create, so Q is some probability measure. And that defines a norm. Namely, the integral of f to the d dp. Usually, the most common choices for p are going to be 1 and 2. But given any probability measure, that defines a norm on function for any q thing. So just think of p as 2, it's this usual alternate. And now what you do is you take your, this is your function space, if only they were really this simple, but let's pretend I can draw it on the board. And you do something like what was just suggested, only it's not going to be an actual algorithm, it's just a kind of a mathematical idea, which is to put down a bunch of points, a net as it's sometimes called, and you put a ball in this norm around each point. So this is each one of these things is a ball around some function f of size epsilon. So it's the set of all g such that in other words, you put down a finite set of points, you put epsilon balls in this norm around them. And now you ask yourself, is this a covering? Does this cover the whole space? So it should be clear that if epsilon is small, I'm going to need a lot of these balls to cover the space. If epsilon is big, I'll need fewer. And n is defined to be the smallest covering, the fewest number of balls you need to cover the space. So that's the smallest, the size of the smallest covering. a measure of the complexity of the space, right? If it's very complex, then you're going to need a lot of these things to cover the space. And this is a very common measure of complexity, and it's very general now. We're not assuming anything of those functions. They're not binary, they're not bounded. So this is an extremely general measure of complexity. And there's a whole series of theorems that are like the theorems we just did that use covering numbers. And the key is that as long as the covering number, it's going to go to infinity or 0, but if it doesn't go to infinity too fast, you can still get bounds. So there are lots of classes of functions that would have an infinite VC dimension or something like that, where that stuff doesn't even work. Where this is well defined and still gives you bounds. Unfortunately, the proofs are a little bit more complicated, so I didn't include much of it. I just want you to be aware of covering numbers. The other thing to keep in mind about covering numbers is you think, how in the world am I ever going to compute these covering numbers? Well, fortunately, starting with Kolmogorov in 1930 until today, people have been working them out. So it's a lot like VC dimension. If you want to know the VC dimension of a particular space, you Google it, and somebody's worked it out, right? It's the same here. All the common function spaces, people have worked out the covering numbers. Actually, I meant to write them down, but I don't think I did. For example, let me give you well, actually, look, I was going to write down some of these covering numbers. I'm probably going to get them wrong, but yeah, I meant to make a list of common function spaces in there. Covering numbers, it might be in the minimax yet, but I thought I could have did it somewhere. So the important thing to understand, here's a couple of examples. All right. Oh no. Let's keep going. Just trust me. You can look them up. So if I give you a class of functions like Sobolev space, remember the functions where the integral of f double prime squared is bounded, things like that. These covering numbers have been worked out. And typically what ends up happening, I'll tell you that if I had a class of densities in a parametric model, so look at a parametric model and look at a set of densities. So you have a parameter space contained in RD. What you'll find is that the covering numbers typically are like 1 over epsilon. That's what a parametric problem is. In fact, you can think of that almost as a definition of what the dimension of the model is. But for non-parametric models, for non-parametric things like Sobolev spaces, they typically look like, and I'm going to go out on a limb here and take a guess. It's going to be something like, for a Sobolev space, I'm going to say e to the 1 over epsilon to some power. They're much bigger. Not surprisingly, right? Because for a non-parametric problem, like a set of all bound densities with bounded second derivatives, we're going to get much bigger covering numbers. Okay, so there is a whole set of theorems that use covering numbers and prove similar kinds of bounds that are much more complicated. And again, we're not going to cover them in class. I just wanted you to be aware of it. So if you see a covering number, just think, okay, it's like a generalization of Rademacher complexity. I did prove one simple bound here, but it's really just the tip of the iceberg. So if you're interested, take a look at figure 7.82. But really, there's a lot of very sophisticated theorems about covering numbers. And similarly, in this realm of, I want you to be aware of this, but we're not going to really cover it, is another type of complexity, which is actually not used much in machine learning, but used a lot in statistics. It's very powerful, and it's called the bracketing number. It's a good thing to be aware of. So the idea is this: a pair of functions, let's say L and mu, such that L is less than mu. The bracket is the set of all functions in between them. So here's L, and here's mu, and every function in between them is called the bracket. So this is a bracket. And now you can ask the same question. Given that I want, suppose I want the norm, let's say uj minus lj, to be less than or equal to epsilon, in what is the smallest number of brackets that cover the space? So in other words, I'm going to take a pair of functions and they have to be no more than epsilon apart in a particular norm, whatever norm you use. Then you pick another pair, and another pair, and another pair, but you've got to make sure you've covered the space, that any function in the space is tracked between at least one of those brackets. Then the bracketing number is usually denoted this way. It's just the smallest size of the bracket. And there's a very precise relation between covering number and bracketing number, which is the covering number, and I'll assume we're working here in the same norm, is less than or equal to the bracketing number and it turns out the bracketing number, again, you can prove these uniform bounds actually much more simply using bracketing than cover. So the field of what's called empirical process theory is all about doing statistics of probability for functions. A lot of the theorems revolve around this bracketing number. Because bracketing gives you very precise control over the function. First, you do a finite approximation of the space. So now you're going to finitely many things. And you can bound everything out above and below by these functions. And so, for example, I put in theorem 7.86. Looks pretty complicated, but it's just Bernstein's theorem, a bracketing version of Bernstein's theorem, is the way to think about it. The very bottom of page 116 gives basically a uniform bound, and it looks like an exponential part, just like the VC thing, but the thing in front now is the bracketing number. And so these things could be finite, even when the VC number isn't even defined. So if you're really into this, I have the whole proof's there, but I'm not suggesting you should necessarily read this. I really, if you're going to focus on anything, the main four theorems, again, are really what the important thing is to take away from the course. This discussion about covering numbers, bracketing numbers, is just extra information for those who are interested. I even put in, if you're interested, a theorem that shows a uniform bound on density estimation, an exponential bound for how far is the density estimated for the true density, and you need to use these kinds of tools to do those sorts of things. So in classification, you can get away with VC theory, but as soon as you get the function estimation things like that, you often need these more sophisticated things. All right. There's a few other goodies in here for those who want to see this stuff. And again, this is totally optional, but I put in something called Talleyrand's inequality, which is a very famous inequality. It's basically like Bernstein's inequality for a set of functions. It was a very big breakthrough when Talleyrand proved that, I would say, in the late 1990s. That's pretty much what we want to cover. So before we go on to the next topic. So again, the main things are really Lufting's inequality, Bernstein's inequality, the VC theorem, and the Rademacher theorem. Those are really, I think, the cornerstones of concentration results. And we may or may not use some of those now for various things like cluster and so on, depending on what we cover. So I want to leave that and go on to the next topic, which is mini-max series. Before I do though, I want to see if there's any questions, because we covered some difficult material fairly quickly. And I want to see if there's questions. Yeah?
So I have a general question, not maybe a foolish question. So whenever we say non-parametric, right, and like you wrote the counting number for the parametric distribution, right? So is it like, is there a parametric family which is non-exponential?
Parametric mean which is not like distribution?
Non-exponential distribution, which is not in the exponential family of distributions.
Are there parametric mean which are not exponential? Oh, sure. Exponential family models are a very small subset of all parametric models.
But are they like studied in machine learning?
Well, let me give you a really simple one. The uniform from 0 to theta. That's the one we got to use in class to show a non-exponential family. Are there other colonies in this model which are non-exponential family? I'm sure there are. Let me see if I can cough one up. Yeah, I think there's zillions. Ryan, is he in offhand?
Isn't coach code, double exponential?
Double exponential?
Yes, that's probably the thing.
Yeah, and then, there's one. And the Gumbel distribution is probably another one. I think there's lots of non-exponential family distributions that actually get used in practice.
So we talked about these sorts of methods for classification and function estimation. So can we apply something like this for learning a graph?
Oh, yes. So where do these get used? So let's say you go to the latest NIPS proceedings and you find some paper about estimating high-dimensional graph columns. And they make up, here's my method for recovering the graph in high dimensions. And now there'll be a theorem that says, under the following conditions, we'll recover the graph with very high probability. Now look at the proofs. It's filled with all of this stuff. So these are the tools that people use to prove all those kinds of theorems. So I don't know if maybe we'll go through some of those proofs and then you'll see where they're used. Yeah, so we have to plan out the rest of the course whether or not to show some of these things. My favorite example that I mentioned already is K-means cluster, which everybody uses K-means cluster to prove that the algorithm, based on data that's coming close to the population algorithm, precisely uses DC theory and mathematical theory. But actually, almost every method is using something like this to show, if you want to prove that it's doing something good when you have a lot of data, typically using some version of concentration measurement.
It's sort of hard to imagine the distance of a graph from the expected.
Well, you probably wouldn't do it directly there. You would first show that the inverse covariance matrix, the one that you estimated, is close to the true inverse covariance matrix with high probability. Let's do a simple little example. I'll just give you an example right now. So where might we use these things? So I won't do the graph case, it's harder, but here's one. I want to estimate, suppose I have a sample from some distribution, and we won't assume anything about it, except in simple, I'm going to assume random variables are bounded, but otherwise arbitrary distribution. And suppose I want to estimate the covariance matrix. So let's use concentration of measure now to prove that the sample covariance matrix gets close to the true covariance. So how do we prove that? Well, the sample covariance matrix will be known by S. What is the sample covariance matrix? Well, every element in here is just an average, some sort of sample average, right? Whose expected value corresponds to the guy in here. And so, let's say so here we go, the probability that the maximum over all entries of Sjk minus Cjk is bigger than epsilon. I'm just going to do the union bound. There's at most, order d squared. Let's say this is a d-dimensional problem. So by the union bound, I can just take the sum over all d squared entries. But for each entry, I'm just comparing the probability that this average minus its mean is bigger than epsilon. That's a sample average minus its mean. So we know from Hoeffding's inequality that that's up to some constant c. And hence, you can see that as long as d, even if d grows with n, as long as it's not growing exponentially fast, this will still go to 0. So what that means is that, so as long as d, let's say little o, e to the n, there you go, concentration concentration of measure shows that the sample covariance matrix approximates the true thing uniformly over the whole matrix, even when it is large. So that would be a simple example of how we use concentration to show that some statistical thing is doing a good thing. I don't know, did that help? Of course, there's much more sophisticated uses of this, but it's pretty good.
So, like this shows that, right, it's going towards the real covariance, right, as n goes to infinity. Do they ever use these kind of things? Like, do they ever actually calculate the constants and say, like, where there's like a 95% chance we're getting the true?
So, I think what AJ is asking is, can we get a confidence set?
Right.
So to do that is much harder, and yes, we do that, but we don't use concentration to measure for that. The reason is, concentration to measure always has these constants floating around. And to know those constants, you have to know a lot about the truth. So typically we use limiting theory. We're going to use the bootstrap to do that, which we are going to have one or two lectures. That's a much more delicate thing to get confidence in. So yeah, this concentration to measure is not really to get confidence in all these things about the procedure. Any other questions? So I'm going to start the minimax stuff then. If you don't have the notes, it's okay, all right. Let me just mention again, that's something I mentioned at the beginning of when I mentioned concentration and measure. I'll just remind you about this, which is if you're very excited about concentration and measure, there is a new book which just came out a few months ago by Massart and I'm going to say Boucheron, but there's like 3 guys who do machine learning in France whose names all start with a B. So it might not be Boucheron, it might be Blanchard or one of the other guys, but I think it's Boucheron. Anyway, and it's called Concentration Measure. The whole book is devoted to concentration measure. And also, Massart has an online book, a PDF book, which contains a lot of this information. So there's lots of places to learn about all this stuff if you want to follow up. All right, great. And let's finally get on to something we have alluded to many, many times throughout the course. We keep telling you, well, here's an estimator, like kernel best estimator, but don't waste your time trying to improve on it because it's minimax. So we sort of have been saying that all along. And we promised you we would show you how to prove that something is minimax. So what we're going to do is go through the basic methods, and then really want to concentrate on one main example, which is non-parametric regression. We want to show you in a particular class, for example, assuming the function says Lipschitz, that how did we get the minimax rate that we claim? And we're going to actually prove it. Okay? So let's first of all remind ourselves what it is. So we have a sample from a distribution. And we'll assume that the P, the unknown distribution P, isn't some class of distributions. It could be very general. Now we want to estimate something, or predict something. Let's say estimate something. We'll call it theta of P. So this might be the density of P. It might be the regression function. Or it might just be a single number, like the mean or the median. Some property of P. Let's, to keep a concrete example of mine, think of doing regression, non-parametric regression, and you want to estimate f, let's say f hat. Just even think of it at one point. I want to estimate the regression function at x equals to 0 or something like that. Just to have a concrete example. So this could be the regression function evaluated at 0, and then we're going to have some estimator, theta hat, which of course is some arbitrary function of the data. One interesting comment I want to make about minimax theory is up until, well, like this year, we always have assumed that theta hat, when we're working these things up, can be any function of the data. One thing that's not been taken account of in minimax theory is computation. And there's just been, in the last maybe year or two, there's been some efforts by some people to say, what if I restrict myself to things that, well, I don't know, have some, aren't NP hard to compute or, things like that. So there's a gap between computational complexity and statistical minimax theory. All this statistical minimax theory, we're not saying this has to be computable and follow along the time or anything. It's just a function of the data. And that's an important gap that's starting to be seen. So we ignore that. We assume we can compute in principle any estimator, and then the minimax risk is defined to be, I take an estimator and I look at, let's say, some distance. We'll say we have some sort of distance function between the estimator and the truth. It might be like squared distance or something else. And so I'm going to take the mean of that, the mean under P. I'm going to look at the worst case over all functions. That tells me the most pessimistic case. What's the worst that theta hat can do? And now we take the minimum of that over all estimators. So again, I mean here all possible functions of x1 to xn. So that's the minimax risk. It sort of says, in some sense, how hard the problem is. This is big, then it's a difficult problem. It's small, it's what's an easy problem. It's a measure of the difficulty of the problem. We've alluded to it many times. But there are two questions that come up. How do I compute this thing? It is not at all obvious how to do this. I would have to think of every possible estimator in the universe, compute the distance, the expected distance, take the worst case over P and somehow minimize over all that. So we're going to have to do some tricks to try to evaluate this, right? It's not obvious at all how to find this minimax risk. And the other thing is, even if I find it, if I tell you the minimax risk is 1 over n to the 1/3 or something like that, I now want to say, can I find an estimator which achieves that risk? Finding a minimax estimate. Okay, so there's the mathematical question of evaluating this, and then there's the practical problem of finding an estimator that achieves that. Now, some people like to express things the other way around. So if I write n here, and if I plot this minimax risk, it will typically go down in that moment. But I can say, how big a sample size do I need before the risk is epsilon? So that's called the sample complexity. That's just n epsilon. You can see it's equivalent, right? If I know one, I know the other one. So some people like to express it as, for a given epsilon, how much data do I need to get the risk down that small? Or conversely, just finding the risk itself. What we're doing is computing risk. So let's, before we go into the techniques for actually computing this thing, let's do two examples. Now I should say that for parametric inference and non-parametric inference, the techniques for doing minimax theory are quite different, and we're going to be emphasizing non-parametric. In 705, did you do some minimax theory? You probably did the parametric case, and it was a strong link to Bayes, right? Bayes, finding Bayes rules with constantness. You're not going to see any of that here. It's all kind of hidden. Techniques are quite different. Actually, let me just remind you, though, of just so we have some concrete examples in mind. Suppose we were dealing with a parametric problem. So that, you have data from a normal theta 1, and suppose your distance function was squared error. So we want to know the inf over all theta hat, sup over all theta. minimax risk, or maybe you were told that the minimax risk is 1 over n. And it's achieved by setting theta hat equal to x bar. Did you do that example? Okay, so there's a simple example. You have a normal particular distance function. We can find this minimax risk, and we can find an estimated risk. A more sophisticated example would be non-parametric regression, where we're interested in, and this is the example we'll do in some detail. And we might be interested in, let's say, the inf over all n hat. So now this is over functions, right? Our estimators in non-parametric regression are functions, they're not numbers. And the soup is going to be over some set of distributions, which could be pretty complicated, right? In particular, we're going to allow, for example, that the functions only be, say, maybe Holder smooth or solo law functions. It's a very large class of distributions we'll be talking about. And then we're going to take some loss function, and maybe one of the loss functions we talked about was L2, for example. This one's much harder, and we gave you the rates for some of these problems throughout the course. They typically tended to be things like 1 over n, 2 beta over 2 beta plus 3, where beta was the amount of smooth is roughly the number of derivatives we're assuming. And so what we want to show you now is how to get back. This is much more tricky than getting the one goal. All right, so let's just jump into it. So when we have a complicated thing like this, how are we going to get it? Well, what we're going to do, the strategy, is to not get it exactly or directly, but rather to track it. So we're going to try to find a lower bound. So we're going to say, well, hopefully I can find some sort of lower bound. Let me call it Rn lower bar. And then we're going to separately find some sort of upper bound. Then you're going to cross your fingers really hard and look at your upper bound and your lower bound. Hopefully they're either the same or pretty close. And then you're done. You get that? Often we only care about the rate, not so much the constants. The constants can be very hard to get. So if this is going to 0 at the same rate as this, then we know what rate it is. I can tell you there's a lot of heartbreak here. Because there's a lot of times you work really hard to get an upper bound, really hard to get a lower bound, and they don't match. And then you're banging your head against the wall because you know one of your two calculations was not tight and you don't know which one. Should you go spend 2 weeks now trying to refine the upper bound or the lower bound? So this can be kind of frustrating sometimes. So let's talk about how do we get these upper and lower bounds. Well, the good news is that the upper bound is often pretty easy to get. In fact, here's a trivial upper bound. Take any estimator at all. And now just evaluate its risk because you've got an upper bound. So just compute, assuming you can do it, compute the average value of that to take the soup. And that gives you an upper bound, right? Because by definition, the minimax risk is the minimum over all possible estimators. So if I take one particular estimator, that's got to be bigger than the risk. So you just pick your favorite estimator. And this isn't as crazy as it sounds, because usually you already have an idea, like I might be a kernel estimator, or I might be doing this, or I might be doing that. But it doesn't always work. So since you asked about covariance matrices, there was some work a few years ago where people did some estimators for inverse covariance matrices in high-dimensional problems, and they worked very hard to come up with an estimator and compute its risk, do this thing. And then somebody came along the next year and showed the lower bound was smaller, and in fact found an estimator which achieved the lower bound, so that showed that the original estimator was not optimal. So sometimes you just take a guess at an estimator and things work out great, sometimes not so good. So this is kind of, I wish I could tell you there was like an algorithm for figuring out what the upper bound is, but really it's kind of an art. You're just going to try different estimators and work out their risk. All right, but we have a technique, we call it, or a strategy for getting an upper bound. Try different estimators and compute the risk. And so we'll do that. In some sense, we've already done this part, right? Because we've taken certain estimators, like density estimators and regression estimators, and we've bounded the risk. So we already kind of have a feeling for doing these kind of stuff. The part that's a little bit unfamiliar, if you haven't done this before, is how to get the lower bound. How am I going to get the lower bound? How am I going to find something that's less than or equal to that? And so, fortunately, although there's many ways to do it, there are really, I would say, 3 very common methods. 99% of the NIPS papers that have lower bounds use one of these 3 methods. In fact, 2 of them mostly. One is called the Tom's method. The second one is called Fano's method. And if you've ever taken information theory, you will have heard of Fano before. The third one, which is Aswad, I probably didn't spell that right, but it's something like that. It's an approximation. But I think we're only going to cover the first 2. So we'll do this one, this one. And they're almost algorithmic. That is, there's certain steps you follow and you'll get a bound. Although, as usual, it's not quite that simple. So let me state a little calm lower bound, or a version of it, I should say. Then we'll prove it. The proof's pretty cool. You'll like it. Well, let's state. So here's this is going to seem a bit odd, but here's what I'm going to do. I'm going to take this set of distributions. This is some huge set of density. Let's just think of estimating a density, and this is all smooth density. I'm going to pick 2 arbitrary distributions here. Let's call them P0 and P1. Let's pick 2. And the theorem is this. That the minimax risk, Rn, is bigger than or equal to delta over 4 times P0 to the n and P1 to the n. Delta is just the distance between that's the bound. So let me just make sure every element here is clear. I have 2 distributions I've chosen arbitrarily from the class. And I'm assuming they have densities little p0 and p1. I now take the quantity of interest, theta, and evaluate it here and here. So maybe it's the density of this, and the density of this, and I'm computing the distance between them. Let's say it's the L2 squared distance. So that's this delta. And now all I do is take delta one more times, and there's this kind of odd-looking quantity, which is called, this is called the affinity. Which is I take P0, the nth, it's the product, measure P0, and I take this, and I take the minimum pointwise, and I integrate. probably looks a little bit strange. And in fact, I'm going to re-express now. There's two other bounds that follow from this bound, which are much more common, which is this is also, this quantity is bigger than or equal to, and I'll show you why in a minute, bigger than delta over 8 times 1 minus half times P0, P1, So let's look at this. So the Lecombe's theorem is this. Now I'm claiming it's actually pretty easy to show that from this is itself bigger than or equal to this. And I'll show you why in a minute. It's just about the fact that when you integrate the minimum of two densities, you can break the integral into two parts. When one is bigger, when the other is bigger, then you start adding and subtracting stuff. And you'll end up with an expression like this. But this thing here gives us a lot of intuition. That's called the total variation distance between the two probability measures. The total variation distance between two probability measures, I'm going to put two versions of it. One way to define it is I take P0 of A and P1 of A and take the maximum over all events. But that turns out to be equal to the expression that I just wrote above. But it's a measure of distance between the two distributions. What this is showing you, so you might be bothered by the fact that I can pick two arbitrary distributions. But remember, this is a lower bound. What we want is the tightest possible lower bound. Remember what we're doing. The strategy is this. In order for this to be useful, I've got to make sure that the lower and upper bound are kind of squeezed together, right? It's easy to get a bad lower bound. 0 is a lower bound. That's not a very useful lower bound. And that's what's going to happen if you don't pick a good P0 and P1. You're just going to get a really lousy lower bound, not tight. The trick is P0 and P1 have to be just statistically distinguishable. It's like we're going to do a hypothesis test between them. And if you can't tell them apart with a test, then you pick them too close together. But if they're too easy to tell apart, you won't get a good bound. So there's a trade-off here. You can see the trade-off now right here. If I want to get a high lower bound. So you think, oh good, I'll just pick them very far apart because that will make this big. Oops, that's going to screw up because then you've just made the total variation distance between them huge. That's going to be like 1. 1 minus 1 is 0. Oops, didn't work. On the other hand, you say, okay, I'll try to pick them a bit closer together. Well, that will help make this term bigger, but then this becomes smaller. So there's kind of a trade-off here between two. So this is sometimes called a least favorable pair of distributions. Just barely can tell them apart, and it's going to give you, if you choose them carefully, will give you a tight lower bound. The other thing, though, I want to show you is another way to write this. So this is bigger than this, which itself is bigger than this, and people often use this form just because this is easier, might be easier to compute and easier to think about. But there's another bigger than or equal to here, which sometimes people use, which is that this is bigger than or equal to also bigger than or equal to delta over 8 e to the minus n KL where KL, I'll remind you, is Kolak-Weidler divergence. So that's the integral P0. I'm sure you've seen this before. It's a measure of distance of two distributions. And again, you see the same trade-off, right? If you make them close together, too close together, or too far apart, you won't get a good bound. In fact, this last version, and I'll prove this. We'll see why is this bigger than this. We'll prove that. This one is not so mysterious maybe, but this one's probably more mysterious. We'll actually include it, it's a good thing to see. But let me just point out now that from that version, we actually get a really, really simple minimax lower bound. This is corollary, those who have the notes, this is corollary 3611. Suppose I pick P0, P1, and I choose them precisely so that the KL distance is less than or equal to log 2 over n. Basically 1 over n. Okay, so if you pick a convenient distribution P0, you find some other distribution P1 whose KL distance is about 1 over n away. Then you plug it into that bound. That bound was valid for any pair, so it's valid for this pair. And so then you get immediately that the risk is bigger than or equal to. If you plug that in there, here, you'll see this comes out to delta over 60. I made that come out to another half. So let me say that again. You take an arbitrary convenient P0. Then you say, okay, I'm going to find some distribution P1 whose Kovac-Weiler distance is about log 2 over n. Now, I find delta, which is the distance of the quantity of interest for these two. And then when I plug this all in here, just plug it in. You get that the minimax risk is delta over 60. What that's telling you is two distributions that are about 1 over n apart in Kovac-Weiler are kind of just barely at the edge of statistical distinguishability. That's what I'm thinking. And that gives us a very nice bound. So we have a lot of backing up to do here because we need to go back and say, how do we prove this, which is pretty interesting actually. And then the perhaps less interesting parts is, how do I prove that this is bigger than S, or how do I prove this is bigger than? And those are a little bit more just calculation oriented. It's good to know all the different versions because, well actually let me tell you why it's good to know. Because sometimes we'll see some problems where it's very easy to compute the Kovac-Weiler distance between distributions, in which case you can see this is useful, right? On the other hand, there's going to be some problems where you'll see that the Kovac-Weiler distance between two things is infinity. That will be useless. And you might want to use this version. So you can see sometimes one might be more useful than the other. Okay, so before we start this proof, let me make sure everybody's with me. Yeah.
Is there a common choice of the function D over there? Suppose we choose D to be this account. Since given that cancels out.
Well, the choice of D is supposed to be based on the problem you're studying, right? So it's what you're interested in. So if you're interested in the L2 error, you use L2. If you're interested in absolute error, you use absolute. So you're not choosing D to try to get a nice bound or something like that. You should think of it as, given this D, how do I find a bound on the error?
But since any of these things actually if you got this in the class, wouldn't that be free of
So D actually, I think, is going to have to satisfy the triangle equality.
Yeah. Oh, okay.
For one thing, but again, really you should think of D as given to you as opposed to.
In a metric space.
I think, if I remember, we'll see when I do the proof. I think I'm going to use the triangle equality, so I think we're going to have to assume that. There are versions actually that okay, so there are other versions that don't assume actually triangle, but the other things then the theorem ends up being a bit different. But the version I'm going to prove definitely assumes triangle. Any other questions?
In practice, how do you go about like finding P0 and P1?
So this is an art, but let's jump ahead a bit to the regression problem, because I'm going to tell you right then how you pick it. So I'm going to show you how you pick it. But honestly, there can be a lot of trial and error, and obviously, many times it can be very non-obvious. But here's how we're going to do it when we solve the regression problem. So later, I guess on Wednesday, we'll find the minimax bound for, say, doing non-parametric regression over the set of Lipschitz. So consider the set of Lipschitz regression functions. Let's say like this. I'm going to take m0 to be the 0 function. That's usually a kind of an obvious first choice. And now what you want to do is pick something which is Lipschitz and which is as close as possible to m0 everywhere except maybe at one point, because we want it to be pretty hard to distinguish. But you have to stay in the Lipschitz class. So a natural candidate for that would look like this, where the slope has to be L. So a little blip, you add a little blip. Let's suppose, we're trying to estimate the function at 0. And this is going to work. This will be a least favorable pair. That we're going to have to play around a bit with the exact positioning and height and everything like that. But that's basically going to be what it's going to look like. If we were doing smoother functions, like twice differentiable, it turns out that the least favorable thing just looks like this. It's got a smoother bump. 0 versus a smooth. So almost all of these groups work like that. You start with a simple function like 0, then you add a little perturbation to it. But you got to make sure it stays in the function class. And then when we're going to do it, we're going to work out the tail distance or the whatever distance you use, and we're going to work with this and work it all out, and we're going to get the lower bound. And then I'll remind you of the upper bounds we did when we did this is no match, luckily. And so we solve the problem. This is what we're typically going to do. That's the strategy. So let me say this is what we're going. I don't want to start the proof now because we want to do this up. So let me say what we're going to do. So we'll start on Wednesday with a proof of Lecombe's method. Then maybe we may or may not prove some of these additional versions that relate the different distances together. We can see about that. But then we want to apply it to regression and get minimax bound. And then I want to talk a little bit about Fano's method. And the difference between Fano's method and Lecombe's method is Fano's method, instead of picking 2, you pick some finite number. You pick, it's like, basically Lecombe's method is like doing a hypothesis test sometimes between P0 and P1. Fano's method is like doing a multiple hypothesis test, P0 versus a whole bunch of other alternatives. And the reason why we want to do that is if all we want to do is estimate a function at a point, or get the minimax risk of estimating a function at a point, Lecombe's method is fine. But if you actually want to do the whole L2 error, you need to consider perturbations like this. You have perturbations all over the place. And that's like considering many hypotheses, alternative hypotheses. And so for L2 error, we use Fano's inequality instead of Lecombe's inequality. This will all make much more sense when we actually do it. Any questions?
You say we showed some numerous methods that we use to say don't bother trying to find that number. We know that these methods are reproducible.
Well, so the question is about admissibility. They're not the same admissibility, and